I know this parts of this will be review for people, and other parts or other people this will be new for. But we want to make sure that we're all using the same notation and we're all thinking about vectors in the same way. So when you first learn about vectors, they're going to say a vector is a quantity with both direction and magnitude. What does that mean? Well, if I think about it, a vector is like an arrow, and the magnitude is the length of that arrow. So, and the direction is just where that arrow is pointing. So think about, to start anyway, think about a vector as an arrow with a length and with a direction. Now I'm, spinning this pencil around as if it's a vector in 3 dimensions. We can start off with a vector in 2 dimensions, and here's how it's written in component form. Here's a vector in 2 dimensions, the vector 3, 4. Its x component is 3, its y component is 4. That means that in the x direction we would go over 3, and in the y direction we would go up 4. Over 3, up 4. It would look about like this. Let's see if we can draw this. Now I'll open Microsoft Paint. Let's not worry about these right now. Let's draw ourselves an axis. And if I go over 3 units, 1, 2, 3, and up 4 units, 1, 2, 3, 4, that's the point 3, 4. And when I talk about a vector 3, 4, I'm talking about the vector that starts 2D shapes line that starts at the origin and goes to the point 3, 4. So we have a beginning of the vector and an end of the vector. Now something to think about though, that's what it is. I can figure out the length of that vector, 3, 4. It makes a 3, 4, 5 triangle. Pythagorean Theorem. This length should be 5. 3, 4, 5 triangle. But keep in mind that vectors can move anywhere. I'm building that vector starting at the origin, starting at 0, 0, and going to the point 3, 4. But once we do that, we've defined its length, it's 5 long. We've defined its direction, over 3, up 4. But now I can move it anywhere and it's still the same vector, as long as I don't tilt it, because that's changing the direction, or shrink it down, because that's changing the magnitude. As long as I don't tilt it or change its magnitude, it's the same vector. We would still write that vector as 3, 4, a 2-dimensional vector in this case. We can also write vectors as, and there's another notation thing. When I write vector 3, 4, I'm using these pointy brackets because I want to say that that's a vector 3, 4, as opposed to the parentheses, which would make it a point 3, 4. Like here, I'm writing vector AB. I got the vector hat on top. Vector AB starts at point A and goes to point B, and I'm giving you what the points are. I know that this is a point 7, 14 because it's round bracket. So if I start at the point 1, 6 and go to the point 7, 14, well, let's think about then what we have. The x was at 1 and it goes to 7. So that's an increase of 6. The y was at 6 and goes to 14. That's an increase of 8. So by saying the vector AB, where I've defined these points A and B, I can say it's vector 6, 8. Oh, which is actually 2 of these vectors. So this vector was 5 long. This is like 2 of those vectors. so it must be 10 long. And we can get that with Pythagorean Theorem as well. So if we're writing vectors in component form, that's like this, where we give you the x-coordinate, we give you the y-coordinate. If it's in 3 dimensions, then we'd also have to give you a z-coordinate. We can express, so writing it in component, we're doing the end minus the start. How did I get that? Let's put that in there. How did we get that 6? Well, I said it started at 1 and went to 7, so we got 6, but that's the end minus the beginning. How did we get that 8? That was the end minus the beginning. So if we have our vectors in component form, or written as vector AB, we can get them into component form by just taking the end point minus the start point. Now I'm written everything in a column here, 3, 4. We could also have written this as a column vector, and that would be where I would write 3, 4 in a column. So let's just pop this in here, 3, 4 as a column. So I need that, and I need what's the difference between a row vector and a column vector? Right now before we know matrices, nothing. So some people express them always as column vectors to make sure they look like vectors. We can write them as row vectors or column vectors. We'll be more specific later on in the course. What's the zero vector? Well, the zero vector is just a vector where all the components are 0. How long is the zero vector? 0. Where does the zero vector point? I don't want to say. I don't know yet. We're not sure about that. We could have 3D vectors. Sure, a 3D vector would be, here's a 2D vector. A 3D vector could be something like 1, minus 1, 0. There's a 3D vector. It lies in 3D space. If you started at the origin, the x would go up by 1, the y would drop down by 2, and the z would not change, so the z would stay at 0. Can you have a 1D vector? You can, I guess, but it's really just, if I write a 1D vector, it's just a number. What's the difference between a 1D vector and a number? Well, a number I'm going to call a scalar number, and a 1D vector then has direction. In this case, there's only 2 directions in one dimension. You're either pointing positively or negatively. So the signs. So I guess numbers are kind of like 1D vectors, where the sign is telling you the direction, and the magnitude of the number itself, the size of the number itself, is telling me the size of it, the magnitude of it. What about 4D vectors? Sure, but a 4D vector, I can't hold anything up and spin it around in 4 dimensions and show you, but algebraically I can write them. There's a 4D vector. What does it look like? I have to point at it and say it looks like that algebraically. We'll learn how to work things, how to work linear algebra in 2 dimensions and 3 dimensions, because we can draw it. But once we know how it works in 2 dimensions and 3 dimensions, then we can extrapolate our methods up to 4 dimensions, 5 dimensions, n dimensions, if I'm thinking about it graphically. But for now, let's stay in R2. R2 is the plane. R2 is things I can draw on a paper. It's the XY plane. So let's take a look at these 2 vectors here. I've got vector A, which I've written in component form, is 1, 2. That means if I start at the origin, I go over 1 and up 2. And vector B, which is minus 1, 1. we want to draw these. So let's open our paint again, and yeah, it's crude. But let's see if we can deal with this. I want vector 1, 2. It's going to go over 1 and up 2. So this is sort of like vector, but I want to make it go over 1 and up 2. So it's kind of like that. It should be over 1 and up 2. It should be how long? Over 1 and up 2. That makes a 1, 2 triangle. I'm going to do Pythagorean Theorem. 1 squared plus 2 squared, 1 squared plus 4, 5. It should be root 5 long. This minus 1, 1 so needs to be shorter, because it would be, well, first let's spin it. It needs to go this way 1 and up 1. So it should be at like a 45-degree angle. Back 1 for the minus 1 and up 1. And it needs to be shorter, because it's only supposed to be root 2 long. So here's vector A, and here's vector B. So what I want to say is, if I go A plus B, the head to tail rule. So that means A plus B. If I add them head to tail, A plus B gives me this vector here, which is some other vector, which I guess I'm just going to draw with a line right now. Be that vector with an arrow on it, starting from here there. Now, I added A plus B, but I could have done it the other way around. Let's see if I can. I could have added, no, I don't want to do that. I could have added B plus A, like that. And that would have given me, get the line, the same vector. So B plus A is the same thing as A plus B. That's our head to tail rule. B plus A equals, A plus B equals B plus A. It doesn't matter what order I add these vectors in. Vector addition commutes. There, trying to write it down. There. Okay. And it makes sense algebraically, right? If I were to add these components to components, I would add the x's. So the x's 1 and minus 1, I would add them together. And I would add the y's 2 and 1, 3. And it doesn't matter if I add the 1 and the minus 1 or the minus 1 and the 1. It's just regular addition. Subtraction. Subtraction, there is no subtraction in vectors. What you're really doing is adding the negative. So in this case, it would be the A minus the B component, so minus a minus 1, 2, and 2 minus the 1, 1. And now it matters what order. So drawing them graphically, I would take, I gotta make that smaller again. I would take vector A, and I want to subtract vector B. So if I reverse this vector, if I reverse vector There. Okay, that was cumbersome. But if I reversed it, I added it. That's a negative b now. The resulting should be the vector 2, 1 over 2 up 1. See how adding them component-wise graphically it helps us kind of understand in 2D, but algebraically, doing it component-wise, that's going to be the way that everything works smoother. Scalar multiplication, if I'm multiplying a scalar, so what do I mean by a scalar? A scalar is a number that's just a regular number, as opposed to a vector. So this 2 is a scalar. I'm multiplying the vector b by 2. So essentially, that'll just be multiply that vector b components by 2. I'm basically taking vector b and stretching it by 2. If the scalar is a negative, well, component-wise, let's see what happens there. That's going to be negative 3. I'm multiplying vector a. Negative 6. That stretches it by 3, and the negative reverses its direction. So it's going the opposite direction of a. This vector minus 3 minus 6 is parallel to that vector and 3 times as long. This vector 2b is parallel to b and twice as long. So some algebraic properties of vectors. So not thinking about them graphically, not worrying about them graphically. This one we already saw, right? The cumulative law of addition, or some people call it the parallelogram law of addition, because if I draw those two pieces together, I'll end up getting a parallelogram. Can we do that? I'll do it like this. So a plus b gets me from here to here, which is the same as b plus a. You get a parallelogram out of it. In this case, I'm getting, I guess, a rectangle, and that's only because I drew a rectangle here. But this doesn't have to be a rectangle. It can be any parallelogram. A plus b plus c is equal to, okay. That looks like I wrote the same thing. Yeah, but what I'm trying to say is that vector addition is a binary operation. You add one vector to another vector. That gives me a vector. That vector plus vector c is the answer to the left-hand side. Or I could have added vector b plus vector c, got an answer, and then added that vector to vector a. So in other words, it doesn't matter what order you add vectors to together. Oh, but it does matter that the vectors are all the same size. So here when I was adding vector a and vector b, they were both two-dimensional vectors. You can't add a two-dimensional vector to a three-dimensional vector. They have to be of the same size. If I add the 0 vector to a vector, it's just like adding 0. You get that same vector together. If I add a vector plus its negative, I get the 0 vector. So if I go out a and then back a, you're at the 0 vector. You get the 0 vector. This piece here is scalar multiplication, so k is a number, a scalar, not a vector. I want to say that it distributes across, so I can distribute it across that plus sign. So the left-hand side, I can take vector a plus vector b, get a new vector, and then multiply that vector by k, or I could multiply the little pieces together and then add vector ka plus vector kb together to get the same answer. Likewise, a scalar can distribute across plus signs. If I multiply the scalar times the scalar 1, well, it does what you think it does. It leaves the vector alone. It's the identity element in vector multiplication. Let's prove one of these rules. And by prove, I'm going to pick a dimension to prove this in, because it's going to be more of a show, I guess, right now. Let's prove this in 2 dimensions. So in general, I'm going to call vector A in 2 dimensions. I'm going to write it out component-wise. That's A1 and A2. And so vector B is the same size, another 2-dimensional vector. So I'm defining this component-wise. And now if I want to prove this, the left-hand side, left side is equal to, all right, and now inside here, let's get the vector A plus B. So the x component would just be A1 plus B1 and the y component would just be A2 plus B2. And now this is just a vector. So here I use the adding vectors together component-wise. And now I can just multiply this k into each piece. So into each component. So that would be k times the first component and k times the second component. And let's work on the right side now. And remember, this proof, this is only good for 2 dimensions. If I wanted the 3rd dimension one, I'd have to go in and add another dimension. In general, you would go A1, comma, A2, comma, dot, 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 AN to prove it in n dimensions. The proof will be exactly the same structure. Now the right side is equal to, the right side of the thing I'm trying to prove is equal to k times vector A, k times vector B. So Ka is going to be, just take vector A and multiply it through by k, component-wise. Vector Kb is going to be, take vector B, multiply it through component-wise. And now I've got this vector plus this vector. I can add them together component-wise, and that's going to give me, well, the thing I have here. Now left side equals right side, so it's proven. Let's work on these in the next video.